Welcome to Andy Hewitt Creations. Today, Andy will show you how to build a camera-controlling robot capable of cramming hours of 3D printing or action into just seconds of smooth, real-time camera movement. Or simply move your camera more smoothly if you want. He will provide downloadable 3D printable models, assembly drawings, bill of materials, code, and wiring diagrams, all while showing you what it can do and how to build your very own for just a couple of Benjamins, or even less depending on what you already have on hand.
And now for the star of the show. So I quickly built this camera robot a while back because I needed a way to smoothly control my camera since my gimbal just wasn't smooth enough. I was making a video on the completion of my Winter 23-24 underwater ROV creation and needed to move the camera in a straight line and also be able to rotate it. I needed to get the video done quickly, so I built it in about a week with mostly things that I already had on hand. I was planning to repurpose it for something else eventually, but when I started making YouTube videos, I realized how valuable it was. I found that I could reduce the speed substantially to create interesting hyperlapses, and later came up with the idea to use it with Octolapse in my 3D printer for 3D print hyperlapses. All these advancements were just cobbled together on breadboard. I also upgraded to better stepper drivers and found that they wouldn't fit my panel enclosure. I needed to build a new panel, and since I don't really have details for it, I'm going to show you my new panel build with the Andy Hewitt Creations Touch to help you with your panel if you choose to build this. I basically just hacked an enclosure that I had used to build an irrigation system controller a few years ago, but since then I've rebuilt it. It was some kind of communications box with a hinged lid. So let's take a look at what I did. I tried to make the controls as user-friendly as possible. I created this diagram akin to what you might see if you purchase something similar for lots of money. The buttons are self-explanatory, but I've broken out the knobs and display. I'm not going to discuss it in detail. Just know that it's available for download, or you can take a screenshot now. Also, just an FYI, the knobs that will do something if pushed have a circle in the middle. So I'm going to go over how to operate this thing as I have it built. When you first power it up, it'll go through the homing procedure. Then you'll set your start position, which will almost always be the home position for the x-axis. For the z-axis, use the Z jog knob to jog the camera until it is pointed where you want. Check in your viewfinder or monitor to verify that it's pointed in the right direction. Then press the Set Start button to set its start position. Next, we set the end position. To avoid having to jog X all the way to the end, I've programmed it to have the initial end position at the near limit of travel, just before the over travel sensor. I almost always want to utilize the full travel, so at this point I just hit the go to end button. Once it reaches the end position, I jog the Z-axis so the camera is pointed at the subject again. Then I verify with the viewfinder. Then just hit the Set End button. I then adjust the speeds of each axis accordingly. You want the displayed travel times of each axis to be the same. In this case, I need to adjust the z-axis speed to be twice what the x-axis speed is because I made some changes to the micro-stepping on the z and I haven't updated the code yet. There's also a multiplier in the code that you can make small tweaks to, but I wanted to leave it as is so I could bring it up here. At this point, everything is set, but I like to hit the Set End again just to be safe. Now we can just hit the Go to Start button and also record at this point if you want. Once the camera's back to start, you can set it to interval or 3D print trigger mode if that's what you're going for, or you can just keep running in continuous mode. And by the way, if you are doing 3D print trigger mode, this should already be set up by your 3D printer and you should already be hooked up at this point before you do any of this setup, because once you power it down, it loses everything. So I'm going to go ahead and show you interval mode. I'm going to set the interval to 10 seconds. I'm going to go ahead and set the layers or number of intervals to 250. I do this by pushing the layers/speed knob down and adjusting it and then pushing it again to get back into the speed. This will advance it 1/250th of that total travel per interval. And then I'm going to let it run, and then I'm going to show you how to pause it, which is to pause during interval mode. All you have to do is just turn that encoder knob to the right, and to unpause it, turn it to the left. So it'll show an indicator on that screen that says PAU for pause in case you want to go do something. When you're in trigger or interval mode, the X and Z screens will go dark. I'll talk about that in the circuit diagram discussion. Okay, so let's take a look at the circuit diagram here. There's really not a lot going on. It might look like it. It's pretty straightforward. In fact, you could wire the whole thing up with just the code pretty much, but let's take a look at this. Let's look at the Z and X axes first because that's what I created first. I didn't have any of this trigger stuff. So in fact, let's cover that up with Charlie here just to keep our attention on this. So we've got our Z and X axes, each of them controlled within our Arduino Nano. These guys are really cheap. I mean, I think you can get a 3-pack of quality, already soldered 3-pack for like $20 on Amazon and have it like the next day. So our inputs for each axis is we have a jog encoder and a speed encoder. And these encoders are going into these serial Wombat chips. They're just 8-pin DIPs. They're really cheap. They're I2C, and they have a library that makes it really easy to read encoders. They've got 4 pins. One of them I think is only used for can only be used for input, but for this is totally fine. So we're going to read the encoders with the serial Wombat. That's going to communicate with I2C. Then we have our switches, which are going to set your start position, you're going to set your end position, your go to start position, and your go to end position. And all these switches are doing is they're just pulling these pins on each Arduino high, and I have pull down resistors here. For the x-axis, we have 2 Hall effect sensors. These part numbers here, all part numbers on here are searchable on Amazon to find these. I plan to make a list too, clickable links. So we're reading these for the over travel and for the homing. And then our outputs here are, we have the 2 LCD displays. They're 20 columns by 4 row LCDs, pretty straightforward. All the codes in there. There's a library that's included in my coding. Then we're also running these two stepper drivers. I started up with TB6600s and they were quite loud and quite slow, and honestly just I wasn't impressed with them. So I switched over to these DM542Ts, much nicer, from Stepper Online. They were bigger, so I ended up having to make a new enclosure, which you'll see in the video. Also, these stepper motors are searchable on Amazon, and I didn't put any color coding for the wires because it comes with documentation. It'll tell you the wire color for A positive, A negative, B positive, B negative. It'll show you that. So then this is our trigger. Okay, this is what I added later. Basically, this part over here is for just moving at a constant rate, moving the X and Z axes, rotating Z, translating X at a constant rate for a video camera to be on board. Or if you wanted to, you could put your camera in interval mode. The key is this is moving at a constant rate over here. The addition of this allows there to be a trigger. When you come over here to the speed encoders and you push the button, it's going to give you a layer option, a layer or the number of intervals. So basically, when you have your start and end positions, it's going to break that into however many layers you have. And you can think of the layers as also how many shots you want to take. So layers, I'm just saying layers because that works for the printer triggering, but also for interval mode, it's still called layers. So it's going to divide your total travel into, say you have 200 layers, it's going to divide your total travel by 200, and it's going to advance every time it's triggered. So over here, this pin 6 is going to trigger both of these to advance forward one time. So every time it's triggered by either the Hall effect sensor or your interval timer, it's going to advance these forward. So that's your pin 6 is connected to both of those. The pin 10, what that does is it says this is in charge. When this becomes in control with either interval or trigger from the printer, it puts these into a passive state. It no longer is reading any of the encoders or the switches, and it's not writing to the display because that's not necessary. In fact, it's going to shut the backlight for the display down just so that you know that that's all dead. You don't want to accidentally turn a knob when it's in the interval mode or accidentally push a button. Pin 10 is going to pull these low. So then we have the Hall effect sensor here is on the printer. We also have an encoder. So the encoder is not going through a serial wombat. I didn't have any, and they are not here yet. So I just read it the old-fashioned way. There's only one encoder. We're reading this Hall effect sensor for the printer trigger. This here is important because you're not always hooked to the printer, right? So if you're not hooked up to that Hall effect sensor, this pin is floating. So we need to pull that up here. You could use an input pull-up, but I like to do physical resistors when I can. If I'm soldering it up and I know I need to pull it up, I'll go ahead and put the resistor in. And this also has an LCD. I'm going to show you how to navigate through the encoder in the menu. There's a very simple menu with this. If you wanted to, you could even have it switch. If you want to do some time stop photography to make animations, put a switch at the same pin, a handheld switch, and you could have, say, a claymation. You could just manipulate that and then take a picture with the trigger, and it'll move it. It'll move the X and Z axis, and it'll take a picture. But the first thing it does is it takes a picture because we want to get that done, especially with the 3D printing. We want that picture taken. We want a short delay so that the picture gets taken. Then we're going to move the camera after that. So there's going to be a delay after the shutter is cycled. Once that's cycled and there's a delay, it will move the X and Z axes. Same thing for the interval. Timed interval is basically the same thing as this trigger, except we're not using that. We're using a timed interval, and you set the time in seconds, and it's going to take a picture on that interval. It's going to advance the X and Z axes to where they need to go, one divided by the layers that you have, and it's going to wait for the next picture to be taken. Pretty straightforward. It'll also count on the display. It'll show you how many shots it's taken. And if you want to pause it, I'll show you later, but you can pause it by turning the knob. It'll pause if you need to do something. We also have a 24-volt power supply, and we have a 5-volt buck converter. Be careful here, because before you hook anything up, power this guy up and use the potentiometer on there. Adjust that pot till you're at 5 volts, because if you don't, I think this thing defaults to 15 out of the box. You will fry everything. So get that set before you even wear anything to it. Then you have it's also got a display if you go with this model. Then we have the camera shutter relay. You're going to have a normally open and the common. You're going to be using those 2 pins. Depending on your camera, I'm using for the stills, I'm using an old Nikon D3200, which has a proprietary plug. And I just bought an aftermarket shutter release that's got a mechanical switch that you can even push and slide for bulb shots. Depending on your camera, you're going to have a different hookup, and you might have to buy a shutter switch to work with that. I haven't figured out how to use my Sony ZV-E1, which I've only found Bluetooth shutter release on that, which I don't want to get into because they require batteries, and you got to make sure your batteries are full, and also the latency of the Bluetooth. And the switches I've worked with, they're kind of finicky, and I just don't trust them. So I'm going to try to find a wired connection. If anybody knows of a wired, somehow I can hook up to the USB-C with a wired USB-C shutter release, leave a message in the comment. But for now, my switch came with a mono jack cable, and I just took that and I cut the cable and I stripped it, and I figured out I needed to hold the focus and the shutter pins to common to get it to cycle. You'll have to do a little bit of testing with that, but that's basically it. Take a look at the assembly. Let's start out with the X travel axis. We're going to have these two linear rails. They're 20 millimeter rails. They're 800 millimeters long. The part number that's on the BOM will include both of these rails and all four of these bearing blocks. Then we have a 8 millimeter lead screw, which it has a 2 millimeter pitch, but 4 starts, which means it's going to have 8 millimeters of travel per revolution of the motor. That lead screw also comes with the lead nut. And then we're going to have 2 bearings. We're going to have a bearing on each end, a flange bearing, 8 millimeter. We've got our 8 by 5 millimeter coupling. We've got our NEMA 17 1.5 amp motor. That pretty much covers, I think, the purchase components. The Hall effect sensors are on the circuit diagram. Then we have some 3D printed components. Everything on here can be 3D printed if you can fit it in your printer. Everything on here is less than 250 millimeters, which fits in my Prusa. The only thing that's not is this. This is 267. So these are 167 by 267 millimeter. But you can print everything. I machined this, and this, but you could 3D print it if you're able to. So we've got the 2 bearing blocks that you'll print, and you've got the motor block, and you've got the carriage block, which holds the lead nut, and also the rare earth magnet here that's going to trip the Hall effect sensors. So speaking of, we've got the home Hall effect sensor, and we have the extend or over travel Hall effect sensor, 3D printable, downloadable, and they're adjustable, and you'll just mount those Hall effect sensors to it. That's about it for the X. Then we'll go to the Z axis. We have all 3D printed components that stack on top of each other. We've got the same coupling. We've got these 2 bearings here that when you print this, that should be set up so that you can press fit these. These have a 22 millimeter outer race, 8 millimeter inner race that you can press fit in there. And then we've got here, it's an M8 all thread that you'll cut. I specify the length of it in the BOM, so that shouldn't be a problem. Then we've just got some nuts here. I had to add a washer here to space. These are M3s. I specify the length in the detail drawings. There are detail drawings that I'll go over with you quickly. Then we have the camera mount here. This allows you to rotate the camera so you can nose up and nose down. So it would be the pitch of the camera. This here is a M6 thumb screw, and that's going into a hole here. This hole is actually designed for an M6 heat set insert. So basically you use a soldering iron. It's brass. You use a soldering iron, you put it in that hole and melt it down from this side. It'll sink right in. That hole is sized for that. There are a number of holes on here that are all sized for heat set inserts. They're all in the details, so you don't have to worry about that, or if it needs to be tapped as well. This, for example, this is tapped. The hole, when you print it, is a M6 tap drill hole size. You'll just tap that M6, snug that down, and then this is what's going to allow you to adjust your pitch of the camera. Then we have this motor's a little different. It's a lower profile, so it can fit in here, and it's also 0.9 degrees per pulse, so it's a little bit finer resolution, which we need on the Z axis. In fact, I'm microstepping 25,000 something microsteps on this, just so we have smooth rotation of that camera. We don't want any bouncing around. Then we have over here, we've got our drag chain.
Feature Andy talking. This time travel's killing me. It occurred to me that I might need to go over what this drag chain / E-chain does. The purpose of it is to carry the cable from your stepper motor to the control panel in a controlled method so it doesn't get hung up on anything. It's also there to carry the cable that you might have for your shutter release, and also if you're running external power to the camera, that cable as well. Because your camera, any cable getting hung up at all or snagged on anything. This is an open loop system, so there's no feedback. These steppers don't know where they are. They just assume that when they take a step, that step has been made. So you don't want to get hung up on anything. So any cable that you have going to that carriage, eventually you want it to run through here. For the cable for the stepper motor, I recommend using a 4-conductor grounded and shielded cable that has an extra wire that you ground at the cabinet only, and that will help eliminate any noise that it may encounter.
In this block here, 3D printable again, it's just here to keep the chain from rising up, because if you were pointing your camera in this direction, it might get up in the way. So this just kind of keeps this all down. All these blocks are 3D printable here. And then we have a 1/4 by 20. This is a 1/4 by 20 hole, okay, which is your typical camera bottom mount threading. But I also have will be available for download. There's some dovetail mounts. I can't remember what they call that designation for that kind of mount, but it's a dovetail shape, okay, and then you can slide, if you've got a dovetail mount on your bottom of your camera, you can mount that to this, and I've got 4 dowels on it that will locate it and keep it square. You can just screw that down there, and then you can quickly take your camera off of there or put it back on. That should make it easier. And then let's talk about the bottom here. So like I said, this is the biggest part. It's 267 millimeters by 167 millimeters. You could, if you wanted to, just go into some whatever software you might have available to modify the step file, and you could just shave this off. If you, for example, had a 250 millimeter envelope, you could cut 17 millimeters off, because these holes here are really just for adding another motor option that I was undecided on at the time, and also mounting my control panel. There's another plate that mounts on here, but I'm going to kind of leave the control panel up to you. You'll have the circuit diagram and all the components. If you want more of that information, just reach out to me and I can help you with that.
I just want to talk about the center plate here. I happen to use 1/4-inch acrylic, and I machined it. All the holes were machined, the dowel holes and everything. But really, these rails are pretty stout, and the dowels aren't necessarily needed here. If you wanted to, you could. This is downloadable as well. You could shave off, because this is 332 millimeters long. So if you wanted to, again, here you could just cut this off in the model just to make it so you can print it, and you can even move the dowel holes over to here so that you can get, because like these 2 holes here, those are 150 millimeters apart. So if you've got, like me, a 250 millimeter print width, you could make this get this down to 250 millimeters. So if you can get a plate in here, that would be a good idea. But you know, you could really probably get away with just slapping a piece of wood in there if that's all you're able to do, and just screw those rails into that. And these rails are stout. You could, dare I say, you might even be able to just leave that out, because you've already straightened everything up. So I wouldn't be surprised if you could just leave this out. But I mean, try to do something here.
More 3D printed components here that just holds the drag chain. It's all in my detail view, and there's part balloons that just show everything. Let's talk about these dowels. These blue dowels are very important. These larger ones are 3/8 inch ABS plastic. You could use acrylic. You could maybe use wood. I think that might have a little too much friction, because these are press fit in here. So when you print this out, you probably want to have the dowels when you print this out or machine it, so that you can check for a press fit. You want it to be press fit into each one. You want some resistance, but you want to tap it in so it doesn't fall out. So what these larger dowels do here is this first rail, this will line up this rail with the plates below, with these plates below, and also since the bearing blocks and the motor block are all doweled to that plate, and everything is doweled to that plate, everything will be located and everything will be straight and aligned, which is very important. The procedure for mounting these kinds of rails is to mount the first rail to a reference surface, which we have with the dowels, and then you're going to assemble this, and you're just kind of tighten these screws down as you slide this thing back and forth. So at that time you won't want to have your lead screw installed, and that's basically how you set it up. But the dowels are very important.
Teacher Andy talking. I think it's important to discuss the point of dowels so you understand why I use them. Dowels locate and orient parts relative to each other. Screws compress parts together, but there is some play. There are always exactly 2 dowels for locating, as 2 points define a line. With 3D printing and or CNC machining, we can place dowel holes in exactly the right place with the same diameter as the dowel. Dowel fitting can be slip fit or interference fit, and anywhere in between, which is transition fit. Exact hole and dowel diameters determine the fit. All fits will locate, but typically one part has slip fit dowel holes and the other has some type of interference fit to keep the dowels from sliding out. With this example, we are properly assembling the 2 blocks with only 1 screw. The dowels keep it from rotating, and you can disassemble and reassemble, and each block will always be in the same exact place relative to each other. You can also use dowels to orient or key parts by placing each of the 2 dowels a different distance from the screw hole, as in this example, also known as poka-yoke.
Also, there are some heat set inserts in these blocks, bearing blocks for the threading. There's a detail drawing that shows you exactly what size goes in there. So when you print it, you can look at that drawing and know what you need. But I will tell you, you're going to need some M3, M4, M5, and M6 heat set inserts. You can get them on Amazon. They're pretty cheap. I think that about covers this. So I'm just going to go over the detail drawings so you know what to expect. I've got the build parts list. This is all your 3D printable or machinable components. These all coincide with file names here. And we've got the purchased component list, and I also hope to have a list for you of exact part numbers and maybe even links to where you can get this. And then I'm showing here that all the electrical component part numbers are going to be in the circuit diagram. I'm including that placard that's on the front panel and all the knobs for the encoders. I've got all these ballooned components here showing you where everything goes. I've got more assembly drawings to show you where everything goes, or some breakout views here. The bottom where the dowels go. Here, for example, I'm showing that's a press fit dowel. This here is for a M5 heat set insert. And when you print this, if this happens to be, this faces on your bed, you'll notice it's going to kind of pucker up a little bit here. There's going to be kind of like a little edge to this that you'll want to just take an X-Acto knife and just chamfer that edge off so that dowel can go in there before you check the fit. Here I'm showing that you need to tap this M5, more press fit, more heat set. So all these things are called out here. M3 tap. Just on all these views, I'm just showing you what all these holes are for, just so you know when you go to machine or print them. Hopefully all this will help you assemble this. Okay, so I'm just going to quickly show you how to set up the Octo print, how to get it to trigger, and the settings that I have. I'm not going to show you how to install Octoprint or set up Octoprint or install the Octolapse plugin. I'm assuming you've already done that and you have everything set up. There's plenty of information out there. So all you need to know is you need to have Octoprint set up with your printer, and you need Octolapse plugin installed. So I'm just going to show you what I did in my settings, and I didn't change much. So just go to Octolapse, and then we're going to go over here to set your stabilization to center right. That's what I did. Logistically, that made sense for me. That's where I put my Hall effect sensor, and it worked for me. If you want to choose something else, that's fine. If something else works better for you. And then what we're going to do is we're going to go to Octolapse Settings. Click the gear, and then we're going to go over to camera. Okay, and then we're going to click the pencil to edit that. And the only thing I have changed is I scroll down here to snapshot delay. I've set that to 600 milliseconds. And that seems like a long time, because especially since they're saying ideally it's 0. But for example, 200 layers, 600 milliseconds, the default is I think 125. So we're talking about a half a second. For 200 layers, you're looking at 100 seconds, which is about 1 minute and 40 seconds. I'm not gonna lose any sleep over that. So that's where I have it set. I'm just playing it safe to make sure that shot is steady and the extruder is in that same exact position every time, and we get a nice clean video. And so you set this here to 600. That's the only thing I've changed, and that should do it for you. I just wanted to talk a little bit about how I mounted my Hall effect sensor on my printer. So it goes up and down with the Z-axis. That's critical. I have a Prusa. I just designed a little bracket that mounts on there with a set screw. That's the black bracket, and it's got 2 set screws. Those are not screwed into that orange plastic. They're just set screw. They're cup tipped set screws, so they're just applying a little bit of pressure. I think I added a little bit of that same kind of 2-sided tape they used to mount phone screens. And then there's another black bracket in the back. And then I have some ABS rectangular hollow tube that I had on hand. And I just kind of threw that together. And then for the other side, I made a mounting bracket that just piggybacks on the fan. And I just removed the screws for the fan and installed that. And then I installed the other black bracket that holds the magnets. I screwed that on there and everything lined up, and I was ready to go. Your situation will likely be different, and so you're really just gonna have to figure out, how do I mount this Hall effect sensor on there? And before you do that, you're also gonna want to get your magnet oriented in the right direction before you mount the magnet. make sure that when you hold it up against that Hall effect sensor that the light illuminates. I really can't gift wrap how to do this. It's just, you're kind of going to have to figure it out. Every printer is different. If you have questions, just let me know. And if you want, I could probably dig up these models for these 3D printed things if you have a Prusa like I do, and I could send you those or make them downloadable. I'm not sure how many people have the same printer as me. So
For my connection from the printer Hall effect sensor to the robot control panel, I just installed a USB-A female breakout on the panel enclosure and soldered the end of a scrap USB-A male cable to the twisted 3-conductor cable to the 3D printer Hall effect sensor. Now I can simply plug into the robot panel when I do a 3D print hyperlapse. I also installed a panel mount barrel jack that's typically used for DC power connections next to the USB, so I can easily plug my camera shutter cable into it.
So that's how you mount the Hall effect sensor. Okay, I'm going to take a quick look at the code here. This is not an Arduino tutorial, or I'm just going to go over the key points. I'm not sure everybody's skill level. I'm just going to point out some things that are unique to this project. So we have 3 microcontrollers. We have 3 files. The X and Z are very similar. The X has homing. The Z does not. I don't have homing on that because the position of where you're pointing that camera is kind of arbitrary and subjective. So looking at the X, we have some well-documented libraries here. We've got the Excel stepper. Wire is for the Serial Wombat because Serial Wombat does not automatically load that library for you. And then we get the liquid crystal, which is that's a very common library. I'll look at the Serial Wombat a little bit because that's not as common. But the first few variables are things that you might change initially when you first build your device. We've got the pulses per revolution. That's going to be your micro stepping settings, and then your millimeters per travel, that's going to be from your lead screw. And then we have an end position. That's just the position it's going to go to when you power it on first and you don't want to jog to the end. That's where that's going to go. And then we have a time modifier. I spoke about that earlier. The speed that you input and the time it takes in real life aren't always exact, and that can be due to loading and other things. So I've just put this time modifier in here so you can make little tweaks to the time sec that is displayed on the screen. This allows you to make little tweaks to that. And we've got some other things here. We've got the position encoder increment. What that is the encoder, when you turn the knob and the Serial Wombat is reading it and it's outputting a value, every click of the knob is 1. But when you're changing the speed, if you just used 1, that would take you forever to adjust the speed. So I have an increment here that's 25. If something larger or smaller fits you, then you can go ahead and adjust that. Same thing for the speed encoder. You can adjust those types of things. It's just basically how sensitive that encoder is for the speed and position. Then we can take a look here at the Serial Wombat, because that's not as common as the other libraries. You basically define your chip, and you'll see in the documentation is a pack of 4, and you get C, D, E, F. Basically, you're declaring this chip, and then in the library, if you have a quadrature encoder, you're going to declare that encoder. So I'm declaring 2 encoders here. That's all there is to that. And then I think again in the setup, we're going to go position encoder begin. Don't get confused here. These are not Arduino pins. These are the pins on the Serial Wombat chip. We're going to go down to the loop. Basically, all the loop is doing is it's looking for this variable set stepper position, and that is coming from the position encoder, or also it could be being incremented from the trigger, the 3D printer trigger. However many layers you have is going to determine how much it's going to increase that set stepper position. Every time there's an increment, it's just going to keep adding to that position and pushing it along as it's in interval mode or it's in 3D print mode. It's just going to push it along. And then we're reading the panel here. Then we have when you go to start and go to end, it's just a loop. And when you hit go to start or go to end, it's in a loop. And once you hit that button, it's in that loop, and it's just going to go to the end or it's going to go to the start. That's pretty much it for the X. Z is very similar. We still have our things that you might change initially or once in a while at the top. And we have the trigger Arduino. The only thing you might be concerned with on this code here is the cycle shutter advance subroutine here. We're going to hold the relay pin high to cycle the camera. And then we're going to delay a little bit. And delay is not a problem with this because there's nothing else going on. But what you might want to look at, and when you're setting yours up with your camera, is the delay for how long you're holding that relay pin high. Your camera might not be as responsive, or it might be more responsive. You might want to decrease that delay time for how long that relay is held high. Basically, what you're doing here is simulating holding the shutter button. Your camera might be more or less responsive. I have mine set to 200 milliseconds. That's something you might want to look at when you're setting up how long you're holding that relay high. That's pretty much it for the code. If I'm seeing that people have a lot of questions about the code, I'll go ahead and make another video. I don't want to overload this video with information. I don't want to make it too long of a video. I just wanted to touch on the important parts. So that's pretty much it for the code. As I shoot a hyperlapse of a winter snow and ice storm out my basement window, I'd like to share some final thoughts. There are many ways to control this robot, and this might not be the best, but the infrastructure is good and potential future code changes may be sufficient to meet my needs if I begin to demand more from it. If I make any major changes, I'll post another video. But everything works well, and only time and more use will tell what, if any, changes are needed. During the initial build, I was considering other options. Having the Arduinos communicate with I2C was a consideration, but in doing that, you have to disconnect the I2C when uploading to the microcontrollers. So I opted to go with simple pin state logic. However, I2C would simplify the inputs and the redundancy of them. For example, I would only have to set the number of layers or intervals once. Also, creating an information channel between the three MCUs would open up new doors. So I may make the change in the future. Ultimately, I really love this robot. It can do things I've not seen before on YouTube. I'm so pleased with the final outcome, and if you're making videos of any kind and are capable of building things, I highly recommend this as a future project. It's a fun build and the results are very rewarding. I've made all files and details available for download, and I can help you with any questions you might have. I built my robot for under $100 initially because I was utilizing things I already had due to time constraints and the fact that I have decently stocked cabinets. I recently looked online to see if there are products out there similar to this and found some very expensive camera controllers costing over 30 times what I spent on mine. Another benefit of building your own besides the cost is the ability to customize it in the future, like I did with a 3D printer layer syncing. I noticed what I found did have lightweight construction, but if that's an important factor, you could try a T-slot aluminum approach, similar to what I used to make my Cheese Curls of Instagram Cheeto photography rig, which would be much more lightweight. And yes, I do have a popular Instagram account dedicated to taking pictures of Cheetos with descriptions of what I see. I'm actually considering making another robot with T-slot aluminum, 10 to 15 feet long, suspended from my shop ceiling and belt driven, so I can do flyby shots. That will be a whole new video. With all that being said, if this build isn't for you, I hope you enjoyed my video and subscribe for more future videos. Please comment on any thoughts this video may have given you. I need as much feedback as possible since this is my first YouTube video. If I've missed anything, let me know in the comments. If you liked what you saw, please give me a thumbs up.
Thank you for watching Andy Hewitt Creations, your personal inventor and design engineer. Hit subscribe to see more videos.